Welcome. This is a do-it-yourself solar charge controller, and uh, the history behind this one is my brother came to me, and he was not happy. He was disappointed. He has been buying charge controllers on the market, and they were failing. Either they would not regulate on the charging, which will actually later on destroy the battery, or not charging at all, and then maybe charging, or and then not lasting long. So he came to me and said, can you please make me a charge controller? I said, okay, I'll sit down and check whether I'll do it within the time that you are expecting. So this is what I came up with: a simple solar charge controller from waste material. From the way you see it now, well, this is actually a hand drone. It's not a computer drone. So yeah, it will be very dirty, but hope I will be able to explain it clearly, as clearly as possible. There are three ways that I've done this. This is the one that I built for my brother, and I called it Mozi, which is my brother's name, and it's Mozi solar charge controller. I've rated it at 12 volt at 10 amps. Until this the date that I've done it. Well, before we start, of course, as always, this is Electronic Waste Benefit, EWB, and to start with the warnings. I emphasize that safety comes first. Electricity can kill. The effects of electricity can cause fire, they can cause electrocution, or you can damage property if you do not take care when you are using electricity. So experience in working with electricity is expected, and prior knowledge of electronics is also expected. If you don't, then look for someone who can actually coach you on electronics. So you also keep work environment and equipment out of reach of children. Minimum age of 10 years is expected for you to try to do these projects. This is the 10th topic and the 15th video that I'm doing on my YouTube channel. Please note, this is not a lesson on electronics, but it's an explanation of how the circuits that I've done work. And please use as much recycled components as possible from waste material, like old PC boards and all that old equipment. There's also ways of doing the project that I've actually explained. You can actually correct it, you can adapt, you can modify, you can improve these free projects, free circuits that I'm giving to anybody. The resources are required. The computer, if you want to redraw the circuit, you may need a computer and software to draw. No, there's no programming here. That is done. You may need a power supply, of course, like any workshop. Electronic components, design, of course, the zero boards, breadboards, and odd boards for components to salvage components, soldering and solder wire, force, and tools, yes, oscilloscope, logic analyzer, nope, not really. Software maybe for drawing Proteus, but well, you can get on the internet. And also, last but not the least, you need to have time, you need to have patience, you need to have passion, you need to have dedication. And feedback, please taramiri@gmail.com. As always, thank you, and I hope you enjoy this one. And going back to our circuit, as you can see, there are three basic areas of concern. There is the control side, and then there is the switching side, the switches, and then the power line, the two power lines, the positive and the negatives. Right, as you can see, the positive, the solar positive and the battery positive are connected together, just straight positive connected, solar positive to battery straight on. Now, and you can see here there is a diode. The diode, the purpose of this diode is for protection. If you reverse your power, the circuit is protected, no current will flow. So we have the diode there, and then the switches are MOSFETs. MOSFETs with a low on resistance, very low on resistance preferred. The ones that can handle also the voltage of the system. The solar module actually get to 22 at most voltage, and the current, depending on the modules that you use, how many and all that. But this is for a 12 volt module, maximum 22 volts expected. Right, and then here this is basically an oscillator, the 4093 logic IC oscillator, to actually switch off the circuit for a moment, so that it checks whether the solar panel is still giving out power, or the sun is still there or not. And then if the sun is not there anymore, the circuit becomes idle. Here the 555 timer is actually control IC. This is control IC, and we'll discuss about the inside of a 555 timer. What we need basically from the 555 timer, if you check it inside, is the comparator and the set reset flip-flop. And the inputs of the 555 timer, they are wired to voltage dividers. So it's wired to voltage divider, and it will actually behave according to the voltage that you set here, the voltage that you set on the inputs. This 555 timer is actually just for indication, basically nothing else, just to show indication. And this is one IC, a dual 555 timer, but you can use single 555 timer. I've done it in 3 ways. This one is the one that I've actually built for my brother, and it's working. And I'll do the other one using a 555 timer for the oscillation, but the rest of the circuit is the same. The third circuit is using 555 timers for sensing. Here, this one uses a relay, a 24 volt relay for sensing solar. The 24 volt relay having a voltage window to switch on at around 15 volts, and then switch out around 13 volts. You can adjust that using a resistor to actually adjust the voltage window here. When it switches on, that's contact in, and switches off, contact out, the voltage that you want. But you know, the battery charges up to maximum 15 volt, 14.9 volts, and will settle down at 12.7 volts and fully charge the battery. And you can check that here, the points to note that the reference for the solar negative has got that sign here. That's the solar negative reference. Here, the battery negative reference is got that sign here. So wherever you see this one, it's a battery negative reference. The IC is powered by 5 volts as a reference. Here, this one is powered by 12 volts from the regulator there. This 12 volt powers this MOSFET. Remember, the gate source voltage should not exceed 20 volts. The solar module can exceed 20 volts, but if the MOSFET gets 20 volts, the gate source, it may fail. So you need to have a regulator there. also to power that one. Also, it is maximum 18 volts for that MOSFET CMOS IC. Sorry, the CMOS IC, of course, that's MOSFET IC. Right. So now the 5 volts is for reference, because here you have 12 volts or 14 volts. You rather have a lower voltage. 5 volts was okay, so that you can actually have a regulated voltage powering the IC. Now, so this is one circuit. Into this circuit, I've built it and it's working. The indication is, you can see we have the solar okay, indicating that the solar is present. This only comes on when the relay is actually being activated. And then we have the regulating indicator here. This is when the battery has reached the 14 volts, it switches off the charging, and this LED comes on to show that it's now regulating. Then we have the battery low voltage. Battery low voltage is a red LED which comes on when the battery is below the set voltage. I've set it at 10.3 volts. It's okay, you can set it to voltage that you want. And then the battery okay voltage, I set it at 13.6 volts, which means your battery is now charged, but well, maybe not full, but charged. You can use the battery. Here I've set the battery to start charging at 13.3. If the battery goes below 30.3 or equal to 30.3, it will be activating the charge signal. If the solar panel module power is there, it will charge. And then when it reaches 14 volts, the other ones I've used 14.7 volts, stops charging, saying the battery is now full. So this is the regulating 555 timer. We'll discuss about the inside of the 555 timer. Next, I'll show you the other circuits that I built. This is the circuit that I will build for myself. The only difference with the previous one that I've done for my brother is this oscillator here. Here I've used a 555 timer rather than a 4093 CMOS IC, and also here I've used a transistor rather than MOSFET. Same relay is there, and you see now the configuration here is different. The rest is the same. This table here is just show the pins for the single 555 timer and the dual 555 timer. Remember, the MC3456 is equal to the NE566. This is a dual 555 timer. Same indication, same components, same MOSFETs. Double MOSFETs here, 2 here, 2, another 2 there. Same set of resistances. So this is one I will build for myself. The only difference is the oscillator, but the rest the same. Right. And then this one, you can do it, you can try it yourself. I have not done this and I'm not going to do this, but I've just put it because I think it should work. The only difference here is it is not using a relay, it's using an optocoupler here. It's switching an optocoupler momentarily so that it checks whether the solar is there or not. Why we check the solar is there or not? Because you normally have a battery voltage here sitting on these rails, and if you do not check, the battery voltage may actually continue to be there even if there is no solar power, and the circuit will be running and you start to have back current. So you must actually check whether the solar is there or not. So I'm using an optocoupler instead of a relay, and I'm using a 555 timer instead of a relay as well. So it's checking on this voltage divider here across the solar panel or solar module rail. So that voltage will actually trigger whether to check for the solar power presence or absence of thereof. And then this one is the timer, just like the one that I'm going to use for my circuit, but the difference is this one is driving this 555 timer. So this one can be a dual 555 timer, or you can use single ones, no problem. The rest of the circuit is the same, no difference at all in the resistance, the resistor dividers. These are just to set the voltages. And how you set the voltages, we'll do I'll show you the way you calculate it. Right, now the MOSFETs, this data sheet for the MOSFETs. These MOSFETs, I found them from the motherboard, computer motherboard, and these are the properties of it. It is having a very low resistance, 4.5 milliohm on resistance. That's very low, and two of them, remember, parallel. That's 2 milliohms. That's almost like just a wire across. That is when it's on, and it's a 30-volt MOSFET. Well, our maximum is 22 at most. And that's okay for a 12-volt system. And 100 amp normally would not get to that, limited by the package. I prefer this package because this one is easier to mount. This is mounted normally on a board, straight on, solder on the tab on board. But this one is easier for pinhole mounting, the heatsink mounting, that is. So I've rated my charge controller at 10 amps, which is okay for that MOSFET. You can use a 32 IRF 3205, IRF 1010, IRF 14. I think it's 1414 or 1411. I don't remember, but any MOSFET with low resistance, maybe up to even 20 milliohms is okay to do the job. And the reason that you do not want resistance or losses at the switch. So these are the switches, so you do not want any loss because of the resistance there. Right, this is the data sheet for the MOSFET, the reason why we choose it. Now this is the inside of a 555 timer, and courtesy of this book here by Paul Horowitz and Winfield Yu, and I bought it I think 20 plus years ago. I got the circuit from there. So it's called a 555 timer because of these three resistors. And remember, this IC is actually a digital IC, it's not analog. What we want is these two comparators and the set reset flip-flop there. And this IC, what it does, it compares these two inputs with the set, sorry, these two, the 2 and 6, compared to the that input and that input. So what it does is, when this number 2 here is lower than 1/3 of the power voltage, 1/3 of that supply voltage, it sets, and then when it sets, the output becomes high, and when it gets to 2/3 of the supply on 6, it resets and this output becomes low. And when this output becomes low, this one is high, this 7 becomes low, the transistor switches on and the grounds pin number 7. So this is how it works, and you can check on the circuitry and maybe figure it yourself. But otherwise, this is what we are using, and we are using it not as a timer, but as a comparator and flip-flop set reset latch. That is in 5 volts. So 1/3 of 5 volts is 1,666 volts or 1,67 volts. 2/3 of it is actually 3,333 volts. So 3,3 volts. So it will trigger at 1,66 and then trigger again at 3,33 volts. So that's why I'm using the 555 timer. This is the inside of it. Right. Now these are the MOSFETs that you can see that they are not new. The metallic tabs are the drain, and they are connected together. This is heatsink, this is metal connected. There are no insulation at all, so this is connected together, and I have actually soldered this drain, the midpoint, together as well, just in case, but otherwise already they are together. They are mounted together, they are together. And then you can see they're old FDP 7045 MOSFET. I got them from computer motherboard. Oh, this one is 1003, I think. This is a, I think this one was what, Intersil 1003, only that one, but the other ones are FTP. These two are Intersil, plus minus the same parameters. What I wanted was just a MOSFET that is low resistance, can handle the current that I've designed for, and the voltage. That's all. They are not new, they are coming from a computer motherboard. They came from the same computer motherboard. Mounted, and also this was okay on their own, these 4 screws, but I've added these 2 just in case. But there's no heat in those because it's low resistance. This is how it looks. Pre-mounted here on wood. There's more heatsink there, and here the enclosure, guess what it is. And then here, this is how it looks. Mounting almost finished, but this was the first mounting and then changed a bit. This is the 4093. I changed it around. It's not how it looks like now. This is the battery negative, the solar negative. Then the battery positive is that red one. It's going somewhere there. Could have been very small wire, of course, but just chose the same size. But otherwise, this could be small, but this must be able to handle the current. There on the MOSFETs themselves. Then the control board there, the relay 24 volt, the regulators one, and the other one, and then the optocoupler, and then the timer, the 555 timers there that I see. Wow. Right. Then here, nice. This is the enclosure. An old DVD ROM from a PC picked up on the dustbin. And that is the indication for LEDs. One is behind there. These 2 buttons are not doing anything, nothing happens there. This is how it looks, plus minus. Nice, eh? Picked up from the dustbin. This one is glued together. I just glued it together. Now one other thing is this charge controller. We have 3 wires: the solar negative, the battery negative, and then the positive for just the control. Remember, the solar positive and the battery positive are just connected straight together. This cable here, the red one, is just for control purposes. This is the one that is going through a diode, remember. So this must be able to handle the current, that one. But this one can be small, no problem. So 3 wires: solar negative, battery positive, negative, and positive. So that's the cables, only 3. So this is how it looks now regulating. This is the battery low indicator. This is the battery charged indicator, battery regulating or battery full indicator, solar present, and that's the battery being charged. And this is my inverter. Remember, there's a video that I did on inverters. That was a sine wave inverter, but this one I modified a bit to come. This is now a square. It's a modified square wave. Yeah, not modified. It's a square wave inverter. But this is the charge controller, and I took this this focus charge controller from there and replaced with the one that I did. I've been running it for 2 months now without a problem at all. This one I break here because the switch there was giving me problems, so I had to use manual switching. This one is one I picked up from, was given by my colleague, and the problem with this one was only a loose contact here which bent the connection. So I just soldered a permanent wire there, but it's working. It's a MPPT charge controller. It's working perfect. These 2 are working perfect. These ones were the ones that I was using. I just took them out was to test from my brother. And I give back the charge controller that I've made to my brother. I'll actually put on this one back before I make my own. When I make my own, these ones I'll put them just for stock, and then I'll be using the one that I'll be building. This is the solar module that is connected to that charge controller. well, it's 90 written here 95 watt, but it's not. This is how I calculate my solar modules. And this is another one. I am using two solar modules. This one is properly rated 55 watts. It's correct. This is another one. It's smaller than the other one, but is a bit smaller. That one is overrated. So the overrated one is 12,3 by 9,5 centimeters. That's centimeters. 12,3 centimeters by 9,5 centimeters. And I calculated down to 70 watts peak because a reputable brand, when you check a 15,6 by 15,6 solar cell, and 60 of them will give you 250. So you compare that to the size of your cells. You can do this whenever you are buying your solar modules. Compare to a reputable solar module and check the dimension of your solar cell, and then compare to the ones that you want to buy, and you can actually calculate the size of the solar module. Derate it by 0.7 because the quality of the cells are actually also questionable. So this one I actually came down to 70 watts, but it's rated 95 watt, but well, this is actually 70 watt if you compare with the dimensions only. And the other one, the 55 watt peak, is correctly rated. This is perfect, correctly rated. Calculated it, came down to 55 watt peak. So these are the two modules, the 55 watt peak and the one rated in 95 watt peak, but your 71 peak. So I have 120 125 watts together. I connected them in parallel, so they're actually giving out 120 watts into my solar system. And yeah, that's plus minus what I can share with in terms of the solar do-it-yourself solar charge controller. And remember, this is just the way I did it, and I'm not saying it's the best way, but I think it's working for me, and it has been working for the past 2 months. I had few problems in the beginning, which I corrected. Of course, you remember, theory is always different from practical. Like here, I had left out these capacitors. If you leave them out, the battery checking voltage here is very tricky. And this is how you calculate your battery settings. Remember, you fix here your resistance. I used 47 kilo ohms. The bigger the better, because we do not want power to be drawn from the battery, because this is always drawing power even if there is no solar or there is solar. So 47 kilo ohms here, and then so you know this is a known quantity. The voltage that you want to set is also known, 14 or 14,7 if you choose. So this will be the voltage that will be sitting there, 14,7 volts. You can calculate one of the input to the 555 timer. Remember, this is the dual 555 timer IC. So the 2 here is not equal to the 2 that is for the single. This 2 is actually that 2 here, which is pin number 6. So here we're looking at the 2/3 the supply voltage. Here we're looking at 1/3 the supply voltage. So don't get confused there. So what we have here is a set voltage. Suppose this is my design, the one that I'm going to build, 14,7 volts that I have set here. So I have 14,7 volts here of the battery. That should say stop charging, the battery is now full. And that 14,7 will stop only when it reaches the 2/3 of the supply voltage. So this is a known quantity, and this set of resistors is fixed. I've chosen 47 volts sorry, I have chosen 47 kilo ohms, such that well, the current that is drawn from the battery is very minimum. You can go to 100 kilo ohms because this will always be drawing current from the battery. So the higher it is, the better. So this 48 is actually 47 plus 1, or whichever combination works for that for you. So this resistor is known, that voltage is known, and the voltage here is known. We have a formula for the voltage divider, which we will do. And what is the unknown quantity is this resistor here. So what are we saying? We'll do it with a paintbrush here to write the formula. Right. The formula is 2/3 of 5 is 10/3, which is 3,33. Should equal to the unknown quantity, the resistance, times, remember, the voltage supply, the voltage that will actually be setting it, that's 14,7 divided by, right, we have to put a bracket here, the resistance plus, so shift plus 48 kilo ohms, closing bracket. Right, 48, I put it 48 here without a kilo ohm, because I know the value that I'll get is always in kilo ohms. So it's 3,3, which is the trigger voltage, equals to the unknown resistance times the voltage which we have set it, divided by the total resistance of the two. That's a known formula for voltage divider. This is the voltage divider, and then you can work out your algebra. It's just as simple as that, and you can do it for that set voltage. You can do it for that set voltage, 13,3, 13,6 if you want, or 13 volts, 13,6, 13,8 if you want. This just to say voltage, the battery is in charged. You can put it 13,8 if you want. You can set it at 13,8. Then here 10,3 or 10,5 or 10 or 11 if you want. You can set it. And please do not forget these capacitors. They are to stabilize the voltages, so that you do not have voltage swinging quickly as the system is working. So this is how you calculate your set voltages. The rest is simple, straightforward. So set your resistors here, and this is one you can calculate. The higher the better, and that's simple algebra. Thank you. And well, this is as much as I can share. The mathematics is not difficult, it's simple, straightforward algebra. To give feedback, and maybe if you have built it and you want to comment or whatever, tauraimidimi@gmail.com. I'll share this one on my Google Drive. Every circuit that I have done, I always put a link on my YouTube channel. There's always a link there. You can actually download from Google Drive. Thank you very much.